Hello everyone, my name is Joon, and I'm here to present our work titled Near Optimal Oblivious Key Value Stores for Efficient PSI, PSU, and Volume Hiding Multimaps. And this is joint work with Alexander Bienstock, Sarvar Patel, and Kevin Yeo. So this talk will be roughly divided into 4 parts. The first part will go over what Oblivious Key Value Stores are and its relation to random matrices. And then we'll then present our OKVS construction called the RB-OKVS, and we'll present some of our experimental evaluations. So what are Oblivious key value stores? So Oblivious key value stores, or OKVS for short, was first introduced. The notion was first introduced by Garimella et al. And is essentially a static key value map data structure. And it has 2 algorithms associated with it. The encode and decode, where encode takes in key set K and value set V, and outputs an encoding of this input. And as for decode, it takes in the encoding and some key K and outputs a value associated with the key K. So just looking at this, you may think that this is nothing really different from regular key value store. So there's a security constraint on it. So as if the values are assumed to be random, then the encoding produced by the encode algorithm should basically hide the keys used to construct this. So why is OKVS so important? Well, it turns out that OKVS turns out to be the fundamental building blocks for many different cryptographic protocols. And notably, it's used in private set intersection and private set union. But in our paper, we also draw connections between the primitive called volume hiding encrypted multimap. So as you can see, OKVS has many applications in different cryptographic protocols. And in many cases, just using more efficient OKVS usually results in more efficient cryptographic protocols that use them. So there are roughly 3 measures of efficiency of OKVS, which is the encoding time and decoding time. And the rate, which is a quantity between 0 and 1, that essentially measures the relative size of the encoding and the size of the original input. So if we look at the prior constructions of the OKVS, we roughly see that either the prior constructions have very good rate, but relatively poor encoding and decoding time, or it has very good encoding and decoding time, but relatively poor rate. So our contributions is more efficient OKVS that can actually get rate up to 0.97, and that has still efficient encoding and decoding algorithm. As you can see, if for our scheme, we have a rate that can go up to 0.97, and it has like a similar encoding and decoding time asymptotically. And to do this, we'll use new techniques from random matrix theory. And plugging in our OKVS scheme into this protocol, cryptographic protocols like PSI, we get a protocol with smaller communication and smaller monetary costs. And plugging this into a private set union protocol, we get a protocol with smaller communication, smaller computation, and smaller monetary costs. And also, if we actually, we also draw connections between the OKVS and the encrypted volume hiding encrypted multimap primitive, and after we plug in our scheme, we get we basically improve upon like previous state-of-the-art schemes. So here we'll go over some relationship between OKVS and random matrices. So this is basically the formal definition of what I actually went over earlier, but essentially the key takeaway here is that we're basically working with some finite field F, and it's basically the same thing as I presented earlier. So there's a concept of linearity in the OKVS, and essentially what that means is that decoding algorithm consists of taking linear combinations of the input encoding. So as you can see, it's basically a dot product of some vector of length m that's applied to the vector encoding E. And linearity is actually used by most state-of-the-art PSI constructions. And there's also a concept of a binary OKVS, which is essentially a more restrictive case where the coefficients of the linear combinations are restricted to either 0 or 1. So what does linearity actually really mean? It essentially, if you actually see, it basically has to satisfy these n relationships. And if we actually represent these as matrices, we get these kind of linear relationships here. So this really means, if you think about it, is that encoding essentially consists of solving the following systems of linear equations. And decoding or batch decoding consists of computing the matrix vector product. So what this really gives us is that our goal essentially is to construct a linear system that is solvable most of the time with only negligible probability and also efficiently solvable, and also admits efficient matrix vector product while minimizing M, or the number of columns, which directly corresponds to a maximizing rate. And then as an aside, the security of the linear OKVS actually follows somewhat like directly from the properties of a solving linear system of equations. So in this section, we'll present our main construction called RB-OKVS. And we'll use the random band matrices constructions from Bienstock and Waltzer. And as I stated earlier, our basically goal to construct a more efficient linear OKVS is to essentially construct random linear systems that are efficient in different regards. And we'll use this construction from Bienstock and Waltzer. So random band matrix construction is actually quite simple. Essentially, for each row, we generate the row as follows. So basically, we fix the interval length W to some parameter W, and then this interval can be just random. And then we only basically put non-zero entries within this interval. So in this example, you can see that the matrices are constructed with W equals 2, and all entries outside this interval will be 0. And there was a theorem proved in the paper by Bienstock and Waltzer. They basically proved that if the number of columns is equal to 1 plus epsilon times n for some epsilon n, and if W is equal to order of log n, then this linear system has a solution with high probability and can be solved in time n times W. But obviously in cryptographic settings, high probability is usually not enough. So in our paper, we extend this and show that if the band length is only, or the interval width is only larger by an order of lambda, then the random matrix basically can be solved with negligible probability in lambda with the same running time asymptotically. And in our paper, we also experimentally determine concrete relationships between the band length W and the security level of lambda. So what this gives us is that this essentially gives us an OKVS with the following properties, where lambda is a security parameter. We get an OKVS with rate 1 over 1 plus epsilon, and encoding times n times lambda, and decoding times order of lambda. And we basically, in this slide, you can see that we plug in our RB-OKVS to the, compared to the prior schemes. And we see that it's basically comparable to state-of-the-art schemes in terms of encoding time and decoding time, meanwhile the rate can go up to 0.97, as I mentioned earlier. So here we'll present some experimental evaluations. So we plug in our Oblivious, we compare our Oblivious key value stores with previous state-of-the-art schemes, and the key takeaway here is that our schemes have in general have slightly slower encoding and decoding time, but we actually gain a lot in terms of rate. And if we actually want to improve the encoding and decoding time, we can actually increase epsilon. So this parameter is actually customizable. This table is probably hard to parse, but essentially what this says is that we actually gain a lot in terms of the communication, but loses some in terms of the computation, except when the network, except when the PSI intersection network configuration is in a slow network, we actually gain more because of the improved communication. And we also plug in our OKVS scheme to a private set union, and we actually basically improve upon prior state-of-the-art schemes. And finally, we plug in our OKVS to the volume hiding encrypted multimap, and we essentially beat prior state-of-the-art schemes in all aspects. Yeah, as you can see here, we basically have the our scheme basically beats prior state-of-the-art schemes in terms of volume hiding encrypted multimap in like every aspect here. Yeah, that's the end of my talk. Questions?